So something happened to the video that we did in class today, so this one is not live, but it'll give you a bit of a sense of a couple of important details about graphing logs. So just going to give you the quick version. This is a little demonstration of what the graph of a log looks like. So you can see that this has a base of 2. So this is log base 2, and that's with no transformations. You can see the a value 1, k value 1, c value 0, d value 0. Okay, and we think of this as, a lot of people will think of this as the inverse of the exponential function. So this would be like y equals 2 to the x. But that would make the y our input and the x our output. So if I put, so 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 3 is 8, 2 to the 4 is 16. But that would be input x, output y, right? If it was an exponential graph, y equals 2 to the x. So you can see that I was thinking of y as my input and x as my output, and that's what gives us the log function. And then it depends on what our base is. So this is our base, and you can see that that if I put some points on here, and if I stretch it vertically, you can see those points are stretching vertically. We're not going to do a lot of changing the k value with graphing, but you can see that it would have the same effect. If I make it really small, it stretches it horizontally, which is hard to graph because those points are going to go off the graph very quickly. And if I make k value big, it compresses it horizontally. So I'm going to put that back. Then c moves it horizontally as always, as we would expect, and d moves it vertically as we would expect. So all those things happen the same way that your gut would have told you to. I'll now change the base to 10 because this is what the textbook likes to use. You can see that we have the same point because anything to the 0 gives you 1. And then 10 to the 1 is 10. So our first point is there. So if I then go ahead and stretch that vertically, we can actually get that point. That will work. But if I stretch it horizontally, it's going to go off the graph really quickly. So that's where we don't probably do a lot of that. Oops, get that back on there. There we go. So the last thing that I want to mention is that I'm going to look at this point right here. So that's this guy, and I'm going to change its color so we can watch it. And as I shift it, notice that it shifts, so it goes, all the points do, but it goes over exactly 3. It goes up exactly 5. And then watch what happens when I change A. Everything moves around it, but it's anchored at that same place. So if I stretch it by A and then move it left a couple and up a few, you can notice that the A still has no impact. This point here, which came from here, went over 2 and up 3. So that's kind of like our anchor point. We certainly don't call it a vertex, but you could think of it like the vertex for graphing these. Now that won't be true with the k value. The k value will move that point, but otherwise, but again, we're not doing a lot of graphing with changing k values for these logarithms. Okay, so that's a quick little demonstration. So how would we actually do this? This is something, these 4 questions are very similar to what you're going to be asked to do in the homework. The first thing is graph the function. I will graph the base function. Notice that it's log base 10, so I will graph this base function. There it is, and there it is, and it comes up and grows very quickly. Okay, and has a horizontal asymptote that is the y-axis, so at x equals 0. Notice that is very important. And really, those are the only 2 points that we can put on this graph because other points, they're too hard to graph or they go off the grid. Okay, so now I have a stretch by a factor of 2, so that's going to move this point up, and then I'm going to move left 1 and down 2. And this point just moves left 1 and down 2, and my asymptote just moves left 1, so it's right there. So this would be the graph of f at x compared to the base graph. Okay, and I'm not going to do question 2. You can see the note for those. State the transformations, very easy, just like we did with all the other functions that we've seen. So you can see the note online for that. For this one, it's also very, very similar to what we've done. I look at the transformation. So what has changed for x? Well, x went to the left 1. And what happened to the y's? I multiplied them by 2 and subtracted 2. So for example, 1, 0 would go to 0, and 0 times 2, 0, minus 2 is negative 2. And my other point, sorry, where am I? Here we go. 10 minus 1 is 9, and 1 times 2 is 2, minus 2 is 0. Okay, so there's that point. And then the domain and range. So again, the base, I'll do this over here, the domain of my base function, x is an element of the real numbers such that x will always be greater than 0. If you think about, and what about y? Y can be anything, so it's just an element of the real numbers. If you think about, again, the inverse of this graph, so y equals 10 to the x, right, the exponential function, it has a domain and range similar, but flipped, because when you're interchanging x and y's, you interchange the domain and range. So the range of that function, of the exponential function, is y is always greater than 0. So for the parent function, for any logarithmic function, no matter what the base is, x is greater than 0. But for this function, the only thing that really is going to change is x is now greater than negative 1. So my horizontal shift will change the domain slightly, but otherwise my domain and range is going to be pretty similar. Somebody asked in class, what about the 10? So the difference between y equals log, let's say, base 2 of x, or y equals log base 10 of x, which is the parent function, isn't that like a change in the function, or a transformation, sorry, in the function? And the answer to that is not exactly. So this is 2 to the x and y equals 10 to the x. That's not a transformation. That's a change of parent function. Now, all exponential functions have similar properties, and the same is true for logarithmic functions. They all have similar properties, but when you change the base, you change the parent function. So then we transform it from there. So you do have to obviously take the base into account. That tells you what your parent function is. So that tells you maybe where the points were originally, and then you transform them with whatever transformations you're given. So that is another thing that can be a little bit tricky with exponential functions compared to the other ones, is we do graph them with different bases. So in grade 11, you do 2 to the x, 3 to the x, 4 to the x, and I think a lot of people get stuck thinking those are transformations, but they're not. They're really just sort of a group of parent functions that have similar properties, so we think about them the same way. Okay, and then the next one, we notice what's different is pretty straightforward again, but it's got a reflection. So that, again, will not impact this point, okay? And normally, I would have a point here, and I would come down like this, but I'm going to transform it, and that point is going to move here, but then it's going to move to the left 5 and up 3, 1, 2, 3, and this point moves left 5, 1, 2, 3, 4, 5, and up 1, 2, 3, and my axis of symmetry, my asymptote, again, starts at 0, starts at x equals 0, and we'll move to the left 5. So it goes to x equals negative 5. And there's the graph of this one, and it shoots up really fast. Okay, and then again, you can see the note for mapping the points is pretty straightforward, and domain and range really doesn't change much here. X is an element of real numbers such that x is still greater than negative 5, and the range doesn't change at all. The only other time that you might see a slightly a slight change in the domain is, and you might have to graph this, or some of the questions might ask about this, is if you have a reflection in the y-axis. So if you have a negative on the x, then that will change this sign, and it'll be less. It'll always be less than. And you could take a look at that with some graphing technology and just sort of see that in action. Okay, and that's about it. Pretty short and sweet. And tomorrow we move on to evaluating logs and looking at some of the laws for logarithms, which is going to be the bulk of this unit.